So, for the material selection project, T19 got a tennis racket. Generally, the tennis racket is going to be incident distress mainly from the strings. So in order to function well, it's going to have to withstand the maximum tension from the strings, not only while it's being strung and tensioned, but also when it's being hit by a tennis ball or whatnot. So functionally, the yield stress must be able to allow the material to withstand all these forces on it and not allow deformation of the material. Moreover, we're going to make a tennis racket that is very good for control. And in doing so, you're going to have very little flex in the frame. When you hit the ball, you're going to want the tennis racket to not bend along the axis. You're going to want it to stay completely rigid so that the energy is transferred into the tension in the strings on the racket and then back into the ball as it rebounds off. It also must be resistant to being dropped or handled roughly. It is a piece of sports equipment and it will be dropped, possibly thrown, and it's nice to have a racket that doesn't break. Moreover, by having a low density, the racket will be lighter and the player will be fatigued slower. And this will allow them to play longer with higher intensity and help them have a better game. Geometrically, the rackets aren't actually constrained very much. The majority of the constraints are made on the stringed area in the middle of the racket. The rest of the dimensions are highly up to player choice and have generally been influenced by player preference. If you want more information on that, you could follow the link to the International Tennis Federation. So our objective here is going to be to maximize the rigidity and yield stress of the material and to minimize the density and cost. So looking at the actual force that's going to be on this racket, we'll be able to calculate the minimum yield stress that the material will need based on an assumed area. So the highest tennis string tension is generally given as 70.5 pounds per string, and that comes out to 32 kilos or 314 newtons per string. You're going to have the highest force acting on the horizontal strings because there are 19 strings, and that comes out to a total of 5.96 kilonewtons of force each side onto the racket. That can be resolved as a single force acting at the center, approximating the forces as a semicircle. So the maximum approximated area is generally 2.5 square centimeters, and this comes from rackets that are currently made out of some composites and older rackets, which were actually made out of wood. Granted, those had a lower tension on the strings, but that is generally what you want and it's what a player is going to be used to. Given those measurements, we can get a minimum yield stress of 23.8 megapascals. So our MPI came out to E multiplied by sigma y over rho times cost per unit volume. So again, we're maximizing the rigidity and the yield strength while minimizing the density and cost per unit volume. The Young's modulus will allow us to have high efficiency and high control in the racket. The yield strength will allow us to keep the sides of the frame quite thin so that the player can very intuitively hit the ball. And since a lot of the dimensions are not set, a gradient of one was used to determine equally performing materials, and that was taken higher and higher up to find the best performing materials. Looking at the Ashby plot, we were left with two options: 2024 T861 aluminum or 5182 H19 aluminum.
So over here, for the sake of the presentation, you can see one of the older versions of the tennis rackets. There's one which is very similar to the one we see today on tennis courts, and at the same time we have a very uniquely shaped one at the back. And you can also have a look at the strings splitting apart, which will play a bigger role in what we're going to talk about in the future. So as mentioned earlier, the tennis racket not only plays a functional purpose, but it also has an aesthetic value. So it's important to go over the possible modes of failure that could affect our tennis racket. The first one is frame fracture, which is caused by the scraping of rackets against the floor or the net. Very, very common during games. Then, especially during doubles games, the second mode of failure is frame breakage, which is the collision of rackets during a doubles game. And this is my favorite type of breakage, which is strings breakage, which is caused due to the smashing of the racket into the ground after a loss, just as we can see angry Serena Williams doing it here. The strings become loose also from continuous impact with the tennis balls and from the impact on the ground. Also, we have the wearing of the grip of the tennis racket due to continuous usage. This leads to a very slippery slope, both literally and figuratively, which makes it very difficult for tennis players to have control over what they do. And last but not least, we have scratching, which is caused either due to scraping, collision, or scratching and smashing. These are some of the possible modes of failure that affect our tennis rackets. And these are factors that we have taken into our MPI index calculations and other factors and arenas where we look at to design the optimum product for the given problem statement.
After using calculations of the MPIs to narrow down to two materials, we have also taken into account properties that were not considered in the calculation of the MPIs, such as cost of manufacture, weight, production energy, carbon dioxide emission, and recyclability. However, for these two alloys, all of those properties prove to be similar. Also, research in manufacturability shows that the cost and effort in manufacturing both alloys are similar. What made us pick aluminum 2024 is that most manufacturer of aluminum 5182 produces only sheets and plates, since the alloy can't be heat treated, whereas the production of aluminum 2024 alloy produces both plates and extrusions. Therefore, we have chosen aluminum 2024 as the material of our tennis racket. So the schedule of finishing process. After we shape and form our metal frame, there are several finishing processes that we have to go through before releasing the product to the consumer. After shaping the metal frame, first and foremost, the frame has to be sanded to remove deep scratches in the surface. This is done before heat treatment to minimize localized stresses and decrease the possibility of cracking, especially during the quenching process when the frame will undergo large stresses. Another reason why this has to be done before heat treatment is that it will decrease the amount of large scratches that will be present after the treatment, increasing the ease of final sanding and polishing before electroplating. Our first heat treatment is solution treatment at 548 degrees Celsius. This is chosen because it was the eutectic temperature and at the highest weight copper percentage of which the alloy can still be age hardened. This is the only temperature that works to create a supersaturated homogeneous alpha solution. So the second heat treatment is quenching. So in this stage, we have to lower the temperature from 548 degrees Celsius to 25 degrees Celsius. This is because after the quenching part, we have to cold work the alloy, and most metals are cold work at 25 degrees Celsius. So the quenching is at 5 to 15 seconds because, as you can see from this curve here, which does not touch the tip of this C curve, 5 to 15 seconds is the optimum time to decrease the temperature from 548 to 25 degrees Celsius. So the third stage of the heat treatment is cold working. This is used to increase the age hardening effect on the alloy rather than increasing the hardness directly. So generally this alloy should be cold worked up to 10%, but 50% is sufficient for the product and the functional requirements of our product. So the last and final stage of the heat treatment process is age hardening. So the alloy should be age hardened at 180 degrees Celsius for 8 hours. This is because 180 degrees Celsius is the highest temperature in which GP zones will still form. And if you can see here in the TTT graph, 180 degrees Celsius corresponds to about an age hardening time of 8 hours, which is not as long as if you have a lower age hardening temperature. The heat treatment will increase the hardness of the racket, which is what we want. So next we have to solve how to minimize corrosion, and to do that we will electroplate the racket after heat treatment. So here we will anodize the racket with mild sulfuric acid. This method has been chosen because it has been used in the manufacture of aluminum tennis rackets since they first started being produced. The final finishing process is painting or powder coating. This is done to increase the resistance against corrosion and abrasion too. The paint or powder coat acts as a second layer against corrosion or scratches and burrs. This is also done to increase the appearance of the product to make it visually attractive.